Oke, Assalamualaikum warahmatullahi wabarakatuh. Selamat malam, salam sejahtera. I will start in Indonesian language, Gabriel. Hola, good morning. So, ada yang berbeda hari ini. Selamat bergabung teman-teman yang sudah mengikuti Berbagi Expert Class. Ada yang berbeda hari ini, kita kedatangan tamu pakar power system yang kali ini datang dari Chile. So I will switch to English now. So today or tonight or this morning in Santiago, the Berbagi Expert Class will be in English. So with us we have Dr. Gabriel Olguin. Good morning. Hola, Dr. Gabriel.
Hola, Mohamed Reza.
So we are actually very happy to have you here. So just to give you a bit about this expert class Berbagi, basically this is a platform to share knowledge from people who have like long experience, relevant knowledge about some engineering topic, scientific topic, and so forth. So today we are going to talk about HVDC technology. I mean, this is an interesting things for us, electrical engineer. As you said, actually before this, we had some chat, me and Gabriel. And Gabriel just told me, like, from all electrical engineers in the world, maybe only 1% do really understand or have opportunities to deal with HVDC. What is HVDC? Why it's so unique in a way? We will hear from Gabriel tonight. And as from this speaker or lecturer tonight, yeah, I can introduce a bit, but I hope you can also introduce later a bit details about you. So I know Gabriel since, I don't know, 15 years ago or more. Actually, when I was studying for my PhD, we met in some conferences at the time. So we are doing our PhD around the same time. And eventually we used to work in the same company in ABB in Sweden, in Västerås. So we became understanding each other more. We know what we are doing. I mean, we have been in some projects together. I remember Mauricio, we supervised together, right? Zhongyu and so forth. So it's the good old days. I mean, times moving. And I think Gabriel left, basically you studied in Chile, in Brazil, in Sweden, and then you work in Brazil and in Sweden, and now you are back in Chile. So we would like also to hear about that from you. It's interesting also for us. I mean, many Indonesians are still abroad, you know, so we also want to listen that perspective maybe for short from you. And since 12 years back, Gabriel has been in Chile, have been working with many studies on HVDC, and just like Indonesia, I think Indonesia is earlier from HVDC discussion than Chile, but yeah, but as you know, HVDC project is not easy to realize. So I will give the screen to you, not the floor, the screen to you, Gabriel. So I think you can start by introducing yourself. Of course, you have time to do presentations, and I hope we will still have some time for question and answers. So please, screen is yours.
Thank you very much, Dr. Reza. Thank you to everyone who is listening to joining this expert lecture. It's going to be, I would say, 50-minute presentation, and hopefully we have time also for questions. Just one slide about me. I'm a power engineer, a bachelor degree from University of Santiago, Chile, a Master of Science degree from Federal University of Santa Catarina, Brazil, and PhD from Chalmers University of Technology. I was senior scientist at ABB Corporate Research Center in Sweden, as Reza mentioned, and then technology manager at Chile's main grid, where I came back in 28 to support the development of HBDC project. Today I'm the president of SIGRE Chile and regular member of a study committee before, which is the study committee that deals with DC system and power electronics. I'm an independent consultant and at a small company called Power Business Limited, a niche consulting firm dedicated basically to HVDC, Hvac, and energy storage. You can visit us as our website. Okay, let's go into the presentation. Well, let me first introduce my country. Chile is a long and narrow strip of land between the Andes mountain. I'm going to use my, let me see my pointer here. Between the Andes mountain and the Pacific Ocean. We have a population of about 17.5 million as 2017. Our capital, which is in the central part of the country, is Santiago. It's the largest city, and our official language is Spanish. Chile borders with Peru in the north, Bolivia to the northeast, Argentina to the east, and the Pacific Ocean to the west, and the direct passage in the far south. Okay, let me tell you a little bit about HVDC experience. I'm going to go through these 4 projects we have been studying. Only one of them has been moving forward, but we have to review all of them. The first project is Hbdc. This is a project that was aimed at transporting 3,250 megawatts. There were 5 hydropower plants in the very south of Chile. And the idea was to move that power to the central part of the country, which is Santiago and the main load. And therefore, we need a very long transmission line. In fact, it was about 2,000 kilometers overhead transmission line with a subsea segment of 400 kilometers. So the only feasible solution was direct current high voltage transmission. During 28 and 29, we undertake a number of planning, engineering, and system studies to design the transmission line, but due to public opposition to the development of hydro resources in this area, the project didn't get the environmental approval, and therefore it didn't go farther. Then we had another project, transmission project initiative, also in the very south of the country, about 400 kilometers north of the previous Hbdc project. Again, the idea was to build a transmission line to transport the power to the central interconnected system, as it was called by that time, the interconnected system. It was a line of 1,000 kilometers, and using direct current high voltage transmission. Again, due to the opposition, to the public opposition for the development of these hydro resources, the project didn't move forward. Another HVDC initiative was the interconnection between the 2 largest systems we had. Before 2018, the Chilean power system had 4 independent electric power systems. The SIN in the north and the SIC in the central south of Chile were the largest of the 4 systems. Chilean government had the idea of interconnecting these 2 large systems to take advantage of sharing reserves and energy exchange. The SIN in the north is mainly thermal, while the SIC is hydrothermal. In 2013, the government finally promoted the interconnection of the 2 systems using the high voltage direct current transmission, mainly because the length of the line. However, at the same time, a private generation company located in the north of the system had already initiated the studies to supply power to a large consumer located in the northern part of the central interconnected system, a project that would require the same transmission line. An international independent consulting company was hired to evaluate both interconnection, and finally recommended the Hvac interconnection because it was easy, or the studies to integrate that interconnection to the system were a little bit easy, and because they already studies, environmental study done by the company. So finally the project was an Hvac interconnection. Such Hbdc interconnection entered into operation just in November 2018. With the new interconnection, of the SIG and SIN, a new large synchronous system was formed, the so-called National Electrical System of Chile, the SIN. Still, Chile's northern region is rich in solar power, and there are also good sites for onshore wind power plants. Since 2014, many solar power plants have been developed and connected to the grid in the north of the system, congesting the existing double circuit 500 kV interconnection. Therefore, a new express corridor for renewable was evaluated and promoted by the Chilean ISO, what we call the coordinador, and our regulatory body, the Energy Commission. And that's why we have today the LACI or Loaguirre-Quimal project. According to the transmission expansion plan, the LACI project will be 1,500 kilometers transmission line from Quimal in the north to the Loaguirre in Santiago. The Hbdc link would be at least 2,000 megawatts and eventually multi-terminal ready. The LACI project will enable express exchange of renewable solar and wind power available in the north with hydro and thermal power located in the center and south of the country. The independent system operator of Chile power system, known as the coordinador, is undertaking the necessary studies to specify the project for an international tender process that would take place in March 2021 with an award in November 2029. Commercial operation of this project is scheduled for December 2028. Okay, but why Hbdc? In order to explain why Hbdc, it is good to use this loadability curve. To explain why Hbdc, we can use the so-called loadability curve of AC transmission line. The concept of loadability is useful in developing a fuller understanding of Hvac power transfer capability as function of the AC line, as you see in this graph. Line loadability is the degree of line loading expressed as a percentage of the surge impedance load of the line, the SIL, permissible given thermal, voltage drop, and stability limits. The concept was first introduced by St. Clair in 1953, who developed transmission line power transfer capability curves covering various voltage levels and line length up to 645 kilometers, based on practical consideration and experience. Later, those loadability curves were analytically derived. Since the loadability of overhead transmission line is expressed as per unit of the SIL, the loadability curve is universal. The curve shows that the value of power that can be transmitted as function of the length of the line is decreasing and is limited by three factors: thermal factor, voltage regulation, and stability. Long transmission lines are limited by stability issues and usually not capable of transmitting more than 1 PU, while shorter transmission lines are limited thermally. Therefore, the longer the line, the lesser the loadability. On the other hand, Hbdc lines has no limit in terms of transmission capacity. So what is Hbdc transmission? Hbdc stands for high voltage direct current transmission, and is just a technology option for power transmission or power exchange between two AC systems or two areas of an AC system. Hbdc uses power electronic devices or power electronic semiconductors to convert AC power into DC power and vice versa, and transmit usually massive electric power over long distances at lower per kilometer transmission line and development costs. In a point-to-point transmission, the order of power transmission and distance are from a few hundred megawatt to few gigawatts, and few hundred kilometers to few thousand kilometers per link. In its simplest form, an Hbdc link is a transmission line with two, I don't know whether I can reduce this. Okay, with two converter terminals. The rectifier station in one end sends power to the inverter station in the receiving end. DC power is transmitted between the terminals by coordinating the operation of converter so that a voltage gradient drives DC current and hence power between the terminals. So how can Hbdc be used in a power system? Depending on the application, Hbdc plays different roles. Most common Hbdc applications are point-to-point transmission, back-to-back interconnectors, and more recently, embedded Hbdc system. In a point-to-point Hbdc application, a long transmission line, either overhead, subsea, or underground, connects two converter stations to move massive electric power between the two isolated systems. In a back-to-back interconnection, the rectifier and the inverter are located at the same place to exchange energy between two systems that, although having equal frequency, cannot securely be interconnected due to stability issues. A back-to-back Hbdc can also enable interconnection of systems with different frequency, and no line is needed since the rectifier and the inverter are located at the same place. An embedded Hbdc link is that interconnect two areas of a power system. An embedded Hbdc link has a big impact on the stability of the system, since by controlling the massive power through the Hbdc link, the power in the rest of the system is also affected, making it possible to better exploit existing AC transmission grid. Okay, let's now review the very basic of Hbdc, the converter. A converter device converts AC power into DC power and vice versa, DC power into AC power. When AC power is converted into DC power, then the converter acts as a rectifier. When DC power is converted into AC power, the converter acts as an inverter. Not all converters can perform both functions, and there are several AC and DC to AC converter topologies and principles. For commercial Hbdc purposes, vendors have selected two basic principles: current source converter, also known as line commutator converter, or just LCC, On the other hand, there are also force commutator converters, or voltage cell converter, or just VSC converters. The conversion process, as you might imagine, is not ideal, nor the AC sinusoidal wave or the DC are perfect. They will contain some degree of harmonic distortion that will require filters. For Hbdc, there are basically two fundamental principles for AC and DC and vice versa conversion. Hbdc LCC stands for a line commutator converter and is the classic Hbdc technology. LCC converters are current source converter that uses thyristor semiconductors in arrays called thyristor valves. When directly polarized, the thyristor valve can be controlled to turn on with a low power pulse in the gate. The turn off, however, can only occur when the thyristor is reverse polarized and the current crosses zero. Therefore, LCC cannot provide black start capability, meaning that cannot energize a passive network. In fact, for proper operation, a LCC converter requires a minimum short circuit level to ensure safe commutation of valve and hence operation of the Hbdc link. VSC stands for voltage surge converter. VSC are force commutated converters that use semiconductors devices with turn-off capability, such as IGBTs. VSC is a more recent converter technology and is still under development. There are a few VSC variants, each one being proprietary of a particular vendor, in particular Hitachi ABB, Siemens, and GE. The Hbdc converter, LCC or VSC, impacts the performance in the AC. Here you have a comparison of LCC and VSC for Hbdc. LCC uses thyristor valve, and while VSC uses IGBTs. LCC is a more mature Hbdc converter technology with the latest development aimed at increasing converter and transmission capacity above 12 gigawatts and 3,500 kilometers in a single bipolar link. LCC advantages are its robustness, low losses, competitive thanks to new OEM suppliers, ideal for overhead transmission lines because the effectiveness in clearing DC faults. However, LCC has some disadvantages, such as the need for reactive power compensation for up to 60% of the rated converter power, need for a minimum short circuit level, need for AC filters to filter out the AC harmonic current. On the other hand, VSC uses IGBTs, which are capable of switching at high frequency. This is the latest and still evolving Hbdc converter technology. It offers some powerful system advantages, such as independent control of active and reactive power, no need for reactive power compensation, eventually no need for AC filter, small footprint, and eventually black start capability. But there are some disadvantages, such as VSC is more expensive than LCC. It has higher losses and some difficulties in clearing DC fault, which makes it not very attractive for overhead transmission line. In this presentation, we will mainly focus on LCC Hbdc converter technology, although we will touch also some applications of VSC Hbdc. So Hbdc LCC is a current surge converter. The fundamental building block of the Hbdc LCC converter is the control 6-pulse converter. However, in Hbdc applications, the current practice is to use a 12-pulse converter, which is built by connecting two 6-pulse converter in series in the DC side, fed by two converter transformers that introduce a 30-degree phase shift in phase voltages. In single line diagram, this is usually shown in this way, or eventually with only one converter, but in practice is a 12-pulse converter. We will see how the converter works in few slides. So let's review the main circuit topologies. The main circuit is the high voltage DC line and high voltage DC equipment. More specifically, the main circuit of the Hbdc system consists of all high voltage DC equipment between the converter valves. The main circuit can be configured in various topologies as required, based on requirements in terms of development stages, reliability, energy, etc. The most basic configuration of an Hbdc link is the monopolar link. In a monopolar link, two converters are connected to a single line. Two converters are connected to a single line, overhead or insulated cable. If it is overhead, the pole voltage is usually negative to mitigate corona effect. The DC current can be carried. Back to the rectifier by land or a dedicated metallic return. Some redundancy can be introduced in the converter station to increase reliability, but the main drawback of a monopolar link is that there is no backup for the transmission capacity in case of loss of a pole line. Another topology is the so-called homopolar Hbdc. In a homopolar Hbdc link, the two poles or more operate with equal voltage polarity, usually negative to mitigate the corona effect. Because the poles are at equal polarity, the distance between the poles is less than in the case of two poles at different polarity, a case we will review next, thus reducing the cost of the transmission line. The return current, however, needs to be rated for the sum of the current in both poles. To my knowledge, there is no commercial implementation of this topology. The bipolar Hbdc is the most common topology. In a bipolar link, two pole lines at different voltage polarity connect four converters, two at each terminal. Due to the plus-minus polarity, the station layout and line top geometry requires electrical distances between the poles, making this topology more expensive than the homopolar. A bipolar link is formed with two monopoles that share the return path, and each pole is independent of the other, except for the neutral and the return path. Main advantage of this topology is the possibility of providing some backup in case of a pole line fall. Most common Hbdc are point-to-point or two terminals links. It is, however, possible to build Hbdc links with more than two terminals. Multi-terminal Hbdc can be monopolar or bipolar. They can use LCC or VSCC technology. And China is currently commissioning a hybrid multi-terminal Hbdc that combines LCC and VSCC converters. Multi-terminals, LCC multi-terminals Hbdc require that the intermediate terminal be equipped with maneuvering equipment to reverse energize the converter according to the voltage polarity and the direction of power in the main converters. Let's now review some possible configuration at each terminal of the link. At each terminal of the link, the converters can be configured to satisfy specific requirements, especially in terms of power and flexibility. Converter groups, for instance, can be connected in series to reach a higher transmission voltage for higher power, or for extra flexibility by allowing a failed converter group to be isolated. The converter connection principle applies to both LCC and VSC. A parallel connection of converter is also possible. Converter groups can be connected in parallel to increase current into the DC line for higher power or extra flexibility by allowing a failed converter to be isolated. Again, this converter connection principle also applies to LCC and VSSC technology. So why transmitting power in direct current? This figure shows the economics of Hbdc as compared to Hvac. The figure shows the development cost of transmission line in AC in red and in DC in green. Hbdc converters are more expensive than AC stations. However, the per kilometer cost of the DC line is less expensive than the cost per kilometer of a AC line. Therefore, beyond a so-called break-even point, the total cost of the Hbdc system is less than the total cost of the Hvac system. The break-even distance depends on many factors, but eventually varies between 600 kilometers and 700 kilometers for overhead transmission line. For insulated cable, it's much shorter, and it might be between 60 and 70 kilometers due to the need to compensate AC cables. Okay, let's get into the mathematics. Let's review the operation of the Lcc Hbdc converter. As I said, practical Hbdc converter uses 6-pulse control converter in series in the DC side, fed in parallel from the AC side. However, to understand Lcc Hbdc converters, we need to review the operating principles of the 6-pulse 3-phase bridge. We will first review the 6-pulse uncontrolled converter based on diode, and then introduce the gate control that is possible thanks to thyristor valve. Consider the ideal 3-phase voltages in this slide and the 6-pulse uncontrolled converter. To understand Hbdc, it is necessary to understand the operation of the gate bridge or uncontrolled 6-pulse 3-phase bridge based on diodes. This bridge is formed by 6 diodes valve. Each AC phase is connected to the cathode of one valve and the anode of the other valve in the same bridge leg. The diode is a unidirectional current conduction device. It allows current to flow when the anode voltage is greater than the cathode voltage, and it blocks when both the cathode voltage is greater than the anode voltage and current drops to 0. Let's consider first the ideal source. That is the case with negligible commutation inductance. So we are going to assume that this inductance is 0. According to the converter circuit, upper valves 1, 3, and 5 share the cathode, while their anode are connected to each phase. Hence, when VA is greater than VV and greater than VC, then valve 1 connected to phase A turns on. The voltage of the cathode of the 3 valves is equal to the voltage of anode of valve 1. Hence, while VA is the maximum voltage, then VP at the terminal of the converter will be VA. Upper valves 3 and 5 are blocked because their cathode are at greater voltage than their anode. Lower valves 4, 6, and 2 share their anode. Hence, VC is less than, hence, when VC is less than VA and VC is less than VV, valve 2 connected to phase B turns on, while valve 4 and 6 are blocked, and therefore N equals VC. Then VPN is equal to a sequence of maximum phase-to-phase or line-to-line voltage segment, and we will see that in detail in the next slide. This slide explains the commutation or conduction period of each thyristor valve in more detail. I have opened the converter bridge for a better understanding. Again, upper valves upper valves 1, 3, and 5 share the cathode, and hence the maximum phase voltage will appear at the converter positive terminal. The maximum voltage will appear here. On the other hand, the lower valves 2, 6, and 4 share their anode, and hence the minimum phase voltage will appear at the converter negative terminal. Since the 3 phase voltages are phase shifted 120 degrees, each upper valve and lower valve will commutate 3 times per cycle. The 6 possible phase-to-phase voltages will appear sequentially at the terminal of the converter. For example, for omega t between minus 20 degrees and minus 60 degrees, the maximum phase voltage is EA, and the minimum phase voltage is EB. Hence, the on valves are valve 1 and 6, and the converter terminal is EAB. For omega t between minus 60 degrees and 0, between minus 60 degrees and 0, the maximum voltage is EA, and the minimum voltage is EC. Hence, hence the on valves are now valve 1 and valve 2, and the converter terminal voltage is EAC, and so on. You can review the complete table. Then the converted DC voltage VPN is a sequence of phase-to-phase voltage segment. The instantaneous DC voltage, VD, at the converter terminal between the cathode of the upper valves and the anode of the lower valve is a sequence of 60-degree segments of line-to-line voltages. The mean or average DC voltage is equal to the integral of the instantaneous voltage over a period of 60 degrees and can be calculated just integrating. So let's omega t be theta, and then for theta from minus 60 degrees to 0, the average DC voltage for an ideal converter without ignition delay is just 3 times the square root of 3 divided by pi times EM, which is the maximum phase voltage, okay? Since the EM can also be expressed in terms of RMS phase voltage or RMS line-to-line voltage, the ideal no-load DC voltage can also be expressed in terms of RMS line-to-neutral voltage or RMS line-to-line voltage. Okay, let's now introduce the firing delay or the ignition control. Hbdc uses a thyristor valve which allows us introducing a delay in the ignition instant of the valve. This ignition delay is known as gate control. The gate control allows to delay the firing of the valve. The delay angle is denoted alpha and correspond to a delay of alpha divided by omega seconds. With delay, valve 3 ignites when omega t equals alpha instead of omega t equals 0. Valve 4 ignites when omega t equals alpha plus 60 degrees, and valve 5 alpha plus 60 degrees, valve 5 when omega t equals alpha plus 120 degrees, and so on. Again, the average DC voltage can be calculated integrating over the corresponding conduction period. In this case, minus 60 degrees plus alpha. Therefore, the direct voltage in the link is Vd0, which is the no-load converter DC voltage cosine alpha. So the effect of the gate control is to reduce the average DC voltage by a factor of cosine alpha. Now, cosine alpha can range from +1 to -1, and which basically means that the DC voltage can now vary from plus Vd to minus Vd. Note that the current does not change direction as the valves are unidirectional. However, the electrical power can change direction by changing the polarity of the DC voltage. We just saw that the LCC converter can produce a negative or positive DC voltage at the terminal of the converter by controlling the valve's ignition angle alpha. The DC current, however, can only circulate in one direction. It cannot change direction because the LCC valves are unidirectional. This slide shows some cases of DC link voltage polarity and power direction. Case 1 is a converter operating as a rectifier. Electric power is taken from the AC system and injected into the DC system. Case 2 is a converter. Note the direction of the converter. Case 2 is a converter operating as an inverter. Electric power comes from the DC link and it is inverted in the converter and injected into the AC system. Case 3 shows an LCC converter operating again as an inverter. Electric power comes from the DC link and is inverted into in the converter and injected into the AC system. Case 4 shows LCC converter operating as a rectifier. Power is taken from the AC system and injected into the DC link. It is important to note that LCC converters works or operate thanks to the AC voltage applied to the valves. It is actually the AC voltage that makes it possible for the valves to commutate. Hence, the inverter operation mode requires an AC system to drive commutation of the valves and current to be injected into the converter. The DC current in the Hbdc line is constant because the large smoothing reactor. Each phase of the system, of the AC system, supplies current to the DC link. The line current in each phase has a squared shape because each valve conducts 2 times pi over 3 radians or 120 degrees. Upper valves feed the positive current to the link, while lower valves carry the return current. The shape of the AC current is independent of the firing angle. Only the phase is affected by the delay ignition, which in turn affect the power factor of the converter, because the phase shift between the fundamental of the current and the fundamental of the voltage. So far, we have assumed an ideal AC source with commutating inductance LC equals 0. For such a case, the AC current commutates instantaneously with no current overlap. Commutation is the process by means of which the outgoing valve reduces its current while the incoming valve increases its current. The figure shows the commutation process of valve 1 to valve 3, while valve 2 keeps in conduction mode. In practice, the commutation inductance LC is not 0, and thus the commutation of current from the outgoing valve 1 to the incoming valve 3 needs a finite time called commutation time. During the commutation, 3 valves are conducting: the outgoing valve, the incoming valve, and valve 2 in this case. The commutation phenomena reduce the average DC voltage in a factor proportional to 3 times the commutating reactance divided by pi. This figure shows a detail of the commutation process between valve 1 in phase A and valve 3 in phase B. Because the commutating phenomena, the converter terminal voltage does not reach the incoming voltage EB. So this voltage should rise up to EB, but that doesn't happen because the commutating phenomena. So just the average outgoing voltage EA and the incoming voltage EB. So that's the voltage that will, so there will be a reduction in the average voltage due to this phenomena, and that can be modeled using this equation. Okay, that's enough in terms of math. Let's go into more in the engineering. Now that we understand the operating principles of the 6-pulse converter, LCC converter, we can now move to understand the 12-pulse LCC converter. The 12-pulse LCC converter is the building block of a monopolar Hbdc link. This is a monopolar Hbdc link. This slide shows the way a 12-pulse converter is made out of 2 6-pulse converters. The phase shift introduced by the converter transformer system allows a more sinusoidal current in the AC side and a more flatter current in the DC side, thus reducing the harmonic filters. A very basic line diagram of a bipolar LCC converter station is shown in this slide. Main components of the converter stations are the Hvac bus bar arrangement, the reactive power and filters in the AC side, the converter's transformer, the valve hole, and the Hbdc jar. Let's review some of these areas of the converter station. The Hvac jar, the bus bar and the breaker arrangement. The Hvac jar is the interface between the converter station and the AC system. Its objective is to enable reliable active and reactive power exchange with the AC system. LCC converter stations need reactive power compensation as well as filter. So this area is where this interconnection is done. The Hvac jar allows connecting all necessary equipment for proper control of active and reactive power exchange between the converter station and the AC system. Because the power involved, the massive power involved, the breaker bus arrangement must ensure high availability and maintainability. Typical arrangement is breaker and a half arrangement for bus bar and breakers. Converter transformers. Converter transformer connect AC bus bar to Hbdc converters in the valve hole or valve building. They are needed to adjust the AC voltage applied to the converter valve to optimize the firing angles. It is a 3-phase voltage transformation system, usually made up of a single-phase transformer of 2 or 3 windings due to transport limitation. It is the largest and heaviest unit of the converter station, and manufacturing and transport restriction will determine its configuration and that of the converter station. The size and the weight of the converter transformers pose a challenge that needs to be addressed early in the project development, since it might involve doing works on road, reinforcing bridges, and so on. Here you have the converter transformers for the converter transformer made of two three-phase two winding transformer. This is a converter transformer system formed by two three-phase two winding transformers. Both primary windings are Y grounded. The secondary winding of the upper three-phase transformer is feeding the high voltage 6-pulse converter group in delta. The low voltage 6-pulse group is fed by the secondary lower transformer in Y ungrounded. The monopolar rated power will go through two three-phase converted transformers. For example, if these were 1000 megawatt monopole, then each converter transformer would be rated at least for 500 megawatts. But if the three-phase two winding transformer were too heavy or too large to be transported to sites or to be manufactured, then the next option is a converter transformer system with three single-phase two winding transformer, three single-phase three winding transformer. No. Yeah, this is three winding transformer. And this would be the general wiring of the three transformer. If the monopolar, again, if the monopolar rated power were 1000 megawatt, then each single phase three winding transformer would be at least 333 megawatts. Again, the primary windings are Y grounded. Yes, right grounded. While one of the 6-pulse group is fed in delta and the other in Y ungrounded. If single phase three winding transformers are still too heavy or too large for transportation, then the only option is to use 6 single phase two winding transformers. Valve hole or valve building. The valve hole is the building which contains the thyristor valve. One of the main functions of the valve hole is to minimize pollution within the hole. Cooling air is required since thyristor and electrical equipment generate heat. The air inside the hole is maintained at positive pressure with respect to atmospheric pressure so that pollution is kept outside the building. This example shows 3 converters transformer per pole side by side with the valve hole. The converter transformer configuration determines the configuration of the valve hole, as we will see in the coming slide. This slide shows a valve hole isometric with the valve legs hanging or suspended from the ceiling of the building. Most common valve arrangements are quad valves and V valves. In the quad valve arrangement, the 4 valves corresponding to each of the 3 legs of the 12-pulse valve group form a column that hangs or is suspended from the ceiling of the building. This arrangement is used when 3 single-phase 3 winding converter transformers are used for a pole. This isometric corresponds to 1 pole in a V-valve arrangement. Again, valves are suspended from the ceiling of the valve hole, and this arrangement is used when 6 single-phase 2 winding transformers are used for one 12-pulse converter group. Inside the valve, you will see 6 valve columns, each one corresponding to one leg of the 6-pulse converter. Station layout. Converter station equipment can be arranged in various ways. Usually the station is clearly divided per pole, as you see here, one pole and the second pole. The dimensions are mainly determined by the rated power, voltage, and redundancy. The largest part of the station is Hvac, with reactive power compensators and filters. The second largest part is the valve hole and the converter transformer. And finally, the Hbdc jar. This Google Earth top view of Loy Yang converter station in Australia. Again, it can be seen that most of the area of the converter station is Hvac equipment, while just a fraction of the area is taken by the Hbdc jar. Finally, here you have a rather compact Hbdc converter station. This is the Baltic cable between Sweden and Germany. This is a monopolar converter station rated at 600 megawatt. The valve hole, the AC filters, and the Hvac jar can easily be identified. So closing remarks. Hbdc technology is a mature technology with more than 60 years of continuous development. There are 2 basic conversion principles for Hbdc today, Lcc and VSSC. Hbdc is especially attractive to transportation of massive electric power over long distance using overhead transmission lines, subsea or underground cable. Hbdc power transmission requires AC-DC conversion, which is performed at the converter station, functioning or operating as rectifier and inverter. That's it, Dr. Reza.
Thank you very much, Gabriel. I think it's a very deep introductory course of Hbdc. I mean, you covered from the studies that you have performed in Chile, and then you touch about the concept of Hbdc, and then some different topologies in the converters, and also the design of the Hbdc. So I think it's a lot for an hour, but I also got some questions from the audience here. As you realize, it's a heavy lecture. So could you please share the slides to us? I mean, you can send it to me.
Absolutely. No, absolutely. Of course, I can share the slide to you.
Yeah, thank you.
And as you said, this is going to be recorded, so it's going to be public there also.
Yes, yes. So for the participants, thanks to Dr. Gabriel. So he will share the slides to us. So he will send it to me. And please fill the participation or attendee list, so then I can inform you where the slide can be downloaded for ones who are interested to download the slides. We have actually some questions, Gabriel, and the time is only 3 minutes. So I don't think this question will be answered in 3 minutes, but I think we will be forgiven to extend the lectures if you don't mind, of course.
No problem.
Yes. Then I will read the questions and let you answer the question. So the first question, I will just switch from question in the Zoom and also in YouTube, because we have some question also from YouTube. Yeah. So first of all, the question is about this length of Hbdc system. So how is the maximum or kilometers Hbdc can be built? So how practical length that probably the longest of Hbdc can be built, or theoretical length that can be built? And what is the criteria? Just what is the criteria and parameter for such technology is feasible to be implemented? So that's the first question.
Okay.
Just go one by one, yeah?
Yeah. As for the length, today we have a 3,500 kilometers overhead transmission line, sorry, in China at plus minus 1.1 or 1,100 kilovolts. That's today, that's existing today. But there are ideas of going up to 5,000 kilometers.
And the following question of that is actually, what is the criteria or parameters to identify or to judge that HVDC technology is feasible?
As comparison to HVAC?
Compared to AC, of course, yeah, I think compared to AC.
HVAC is a wonderful technology and it has solved many issues. I always say that it's not a matter of selecting the technology. I mean, HVDC is not for every application. Hbdc, direct current transmission, is for long interconnection, is for asynchronous interconnection. And today it's also seen as an enhancement of the AC system because it's a controller. You see, when you have an AC system, the system is it's responding to the inertia, is responding to you know, the dispatch that has been scheduled and so on and so on. When you have an HVDC, a line embedded in the system, then you can control the rest of the system also, because whatever you do in this digitally controlled device, which is a huge device because we want to move maybe 2,000 megawatt, 3,000 megawatt, quickly enough, you are giving a lot of controllability to the system. So today it's also seen as a, well, actually it is a Hvac, it's a flexible AC transmission controller. You are using power electronic and digital control to control massive power, which is part of an AC system. So it's also an enhancement of the controllability of the system. Yeah.
And we'll go to the next questions. So how about the transmission tower? I mean, if you are talking about overhead lines, HVDC, can we use the existing foundation of HVAC tower? I think there's a question also in YouTube, just let me make sure. Yeah, exactly. So can we actually switch from HVAC, the structure, tower, etc., to HVDC?
There have been a couple of attempts to do that. And also some initiatives also in our country. One of the 500 kV transmission line that interconnect the north and the south in the annual transmission expansion plan was proposed to be changed to DC, just to increase the transfer capability of the corridor. I don't know, I think it's possible, but you have to review the line. You have to review whether you can do it, because actually, whenever you want to push more power into an existing corridor, is because that corridor is already congested. So you cannot take it out of service to do what you want to do. So usually it's very difficult to, you know, to transformate an AC line to DC, but technically speaking, it's possible.
In the 4 projects that you mentioned in the beginning of the lectures or your presentations, are those 4 projects are a greenfield, or is there one converting HVAC to HVDC?
No, those were development projects that nothing was done before that. I mean, those are hydro resources located in the very south of Chile. It's a sort of pristine area, you know, untouched so far, and that's why it was very difficult and it was impossible to get social acceptation of the project.
I see. I see. And I think this is a good question from YouTube. The question is like, when we are implementing HVDC technology, do we require specific materials for the copper and for the insulations?
No, it's I mean, as for copper, is copper. Insulation, I mean, DC insulation behaves a little bit different than AC insulation, but it's basically the same sort of insulation. As for overhead transmission line, usually they use glass insulators, but nothing special, I mean, I would say.
So it's the same conductor. I mean, basically the same.
Oh yeah, yeah. In terms of conductor, is I mean, you can use even the same conductor you use in AC lines, but not copper. Today, nobody uses copper for overhead transmission line. It's aluminum, steel reinforced, those kind of wires for overhead transmission line.
Yes. Okay. So we move to the next questions. Yeah, this is actually you have answered, but this is more like, is there any, yeah, the question is like, what is the difference in the insulators between HVDC and HVAC? I think, as you said, the materials is probably, and the design maybe, or what is from your study experience?
Inside the valve holding, inside the valve hole, I mean, since it is an indoor environment, you can really control the environment in terms of pollution, and insulation inside is kept, I would say, in very good shape. I mean, you don't really match insulation, although you use a lot of over voltage protections, arresters, and things like that. But insulation is kept rather short, I would say, because it's a very clean environment. Outside in the DC line, well, is as any overhead transmission line, the insulation will get contaminated, and one of the pole actually is going to be more contaminated because it attracts pollution, like a DC positive pole. But I mean, it's something that needs to be studied, and you will select the right insulation, the length of the insulation string and so on. But it's basically the same engineering concept.
Yeah, yeah. Great. So now is about the grounding systems. I think you have explained in the slides. So I think this is probably given when you were presenting about this grounding. So I think the question is like, could you please explain a little bit more about the system grounding that is used in your HVDC, so in LCC HVDC, I guess, yeah? Yeah,
when you remember that I was presenting I was calling it the return current. I mean, the current that comes back from the inverter terminal to the rectifier terminal. We have to close the circuit. We send the current to the pole, and we need to bring the current back. That current can be brought back through earth return, which basically means that you will have two earth electrodes, one at each terminal, and you will inject the current into the earth and get it back in the other electrode. This is something that has been done in many projects. In Brazil, is rather common. In Sweden, and some of the projects between Sweden and Baltic Cable and others use C return. So basically they have C electrode. But in some cases, using earth return might be an issue. I mean, it might have impacts in, it might be, underground infrastructure, for instance, and so on. There are many impacts that should be studied in order to design ground electrodes. So in such cases, when you cannot really use earth return, then you would need to put metallic return, a third conductor between the neutral point of both terminals, the rectifier and the inverter. And that is called dedicated metallic return. For instance, the project that is being moving forward in Chile is indicated with dedicated metallic return because, because there are some opposition to electrode, especially if it is difficult to find good, resistivity, because you need a very good site to inject the current deep in the earth so that you have a very low resistivity or grounding resistivity.
Yeah.
So that's more or less, but it's a complex matter, but it has a lot of engineering already developed, and there are many ground electrodes, also C electrodes around the world.
Sure, thank you. And next question, I think it was also given when you were giving your presentation, is about the short circuit capacity. Why do we need to consider short circuit capacity for LCC HVDC technology? And why is not the case for VSC HVDC?
Well, hopefully it was clear during my presentation. I mean, I was trying to explain how the thyristor valve commutate, and I was explaining that you need an AC voltage that drives the commutation. If you don't have an AC voltage, then you will not get commutation.
In LCC, HVDC.
In LCC, I mean, LCC based on thyristor commutate because you need, because you have an AC voltage that is producing the commutation. If you remember the table I was showing, the commutation happens because you have AC voltages. So if there is no AC voltage, there is no commutation. And that basically is short circuit. I mean, a dead grid has no short circuit. So the higher the short circuit level, the stronger is the system and the better is the commutation. That's the basic concept. And there is a number, an index, which says that it should be between 2.5, I mean, greater than 2.5. I mean, in terms of the ratio, effective short circuit ratio is called. I mean, the short circuit capacity should be at least 3 times, more or less, the capacity of your link or your converter. Say you have 1 giga transmission capacity, you need, in order for that LCC converter, 1 giga LCC converter, you need a short circuit capacity of at least 3. Of course, those things can be changed with controller features, and vendors are doing a lot to improve that, but that's more or less the number, 2.5, 3.
Yeah, and the question is, how about the VSC technology?
VSC, it's a force commutated technology, and therefore it doesn't need AC voltage to commutate. I mean, you do have control to turn on and off each one of the IGBTs, and therefore you can sort of create the sinusoidal signal. And that's why you don't need the short circuit capacity. You don't need AC voltage to drive the commutation. You control the commutation on and off. And since you have the control to turn on and off each one of the valves, you can do a lot of things. And one of the things you can do, you can create an AC signal. Mm-hmm. And you can create you can move, you know, in terms of magnitude, but also in terms of shape. And that gives all the beauty and all the controllability you have within DSSC converters.
Yes, and I think it's related to another question also. I will, because it has some common, like based on the situation in Sumatra, Java, in Indonesia, HVDC project that was postponed, there was short circuit issues that would increase with the operation of 1,000 megawatt power plant, large scale in Java. So the question, like, is it feasible if we use HVDC just for back-to-back function or converter station only, comparing to fault current limiter technology to reduce short circuit level, which increased due to many new generations. So I think the question is like, can we use this HVDC back-to-back combined with the fault current limiter technology to reduce the short circuit level due to, let's say, a lot of generations of power plants connected to the
HVDC is also, I mean, it has been recommended as a short circuit limiter. I mean, when you really need to do an interconnection, and if you go for AC interconnection, then you are going to increase the short circuit capacity, which basically means you will, you know, need to change all the breakers. So eventually, an Hbdc interconnection might reduce the short circuit capacity because you don't contribute to the short circuit with an Hbdc. But to be honest, I haven't seen such application.
Thank you, Gabriel. And here is another question. It's about, I think this is also maybe given while you were giving your presentation. It's a question about what is the function of upper and lower valve for this HVDC. How is about the voltage input of upper valve? I think this is when you were explaining about this upper lower valve of HVDC. So the question, what is the function?
I mean, the converter, the LCC converter, is based on 6-pulse converter, the classical 3-phase full converter. And in order to refer to the valves that are in the upper part of the converter, I say the upper valves and the lower valves. But that's it. I mean, it's just the 3 valves that are in the upper part and the lower part.
Sure. Thanks. And now a question about the protections. Because you have also mentioned about the design. What is about the lightning protections of HVDC? Maybe we're talking about the...
Yeah, lightning is a very, well, lightning is, as in AC, is something that is very difficult to avoid. I mean, in order to avoid lightning, you will protect the line with, you know, wiring, ground wiring. That's the name. You know, the cable you put on the top of the tower in order to receive lightning. But even if you go for that, you will get some lightning stroke directly into the poles. Those lightning will eventually be seen as a ground fault of the DC line. And any ground fault will be seen by the control, and the control will react. It's not a protection properly as you might think in a AC line. It's the control that will see that increase in current and will react in order to reduce the current, to reduce the voltage, to deionize the line, and then restart the line, the converter and the line.
Yeah. And want to add more?
I was about to say that in terms of AC protections, is the classical AC protection. I mean, the breaker and a half arrangement will have their protection. The converter transformer will have differential protection, and so on and so on. So the AC part is classical AC protection, and the DC is protected using the control, mainly the control, because it's quick enough to protect the system. I mean, you have a semiconductor, in this case, a thyristor, that is able in half a cycle, basically, to interrupt current. So you will use that in order to protect the system. Of course, there are many other protection inside the valves, especially for overvoltage and things like that. But the classical protection is that.
And here is a question like how HVDC is used as frequency converter. Maybe this is like, since it's a flexible, as you mentioned in the beginning, it can connect like two systems with two different frequencies. So
interesting, but
how does it work? Yeah.
Actually, again, it's not that the converter imposed the frequency to the AC system. It's the AC system that produced the commutation of the valves. So if you have, say, as in our case, we have Peru, and Peru is 60 hertz, and we are 50 hertz. So if we put the back-to-back interconnection, the 60 hertz AC system will drive the commutation of the 60 hertz converter, basically, and the 50 hertz system, AC system, will drive the commutation of the 50 hertz converter. So it's not that we control the frequency, but it's that the AC system will drive the commutation. So that's why you can enable transfer of power between two systems that have different frequency.
Great. Yes, thank you for the explanation. And now a question about the cost when we are comparing AC and DC transmission lines on point-to-point or multi-point connection. Because of multi-point connection, over 700 kilometers, for example, AC transmission line could be cheaper than DC because it does not need converter terminal. So from the cost comparison, point-to-point or multi-point connection, do you have any comment on that?
Well, the comment is that the longer the interconnection, the more attractive Hbdc might appear. Because what really sort of makes the difference between an HVAC and HVDC interconnection is the line, the transmission line. So the longer the line, the more attractive is HVDC. And the break even is, 600 kilometers, 700 kilometers. It really depends on how much you really pay in the place, because land might cost more or less depending on the country, And for instance, in the north of Chile, it's very unpopulated. It's a desert, so it might be cheap, the land. But in the south, it's much more dense populated, and it's going to be much more expensive.
And how about multi-terminal HVDC? You have any comment compared to, let's say, grid AC or AC grid?
Well, today there is a lot, especially in Europe, there is a lot of not only research, but actually engineering and application of the DC grid idea. And vendors are moving into that direction. And the idea is to move from multi-terminal to a DC grid. Now, a DC grid is something completely different than point-to-point or multi-terminal HVDC, because the idea is that as we have in the AC grid, we built a DC grid. That needs some technology that vendor says that it's ready, like DC breakers, but there is no commercial application yet. In the future, there might be, and in that case, the idea will be to have a real DC grid, so that power can be transmitted. And in the case of a line fault, then you move the power from that line to another line and so on. As the way it works, the AC grid. Because in the AC grid, whenever we lose one line, the system reaccommodate to keep feeding the load. If we move to a DC grid, it's going to work in the same way. And that's the idea. That's the effort that vendors and ISOs are doing in order to move into that direction, especially in Europe, because offshore wind farm and the way they are interconnecting this. If you look at an offshore wind farm today, you are bringing the power from an offshore wind farm through a cable, only one cable. So if that cable fails, you end up without the power. So the idea is that you build a grid, a DC grid. So in case you lose one cable, the power can be redirected to another path to the continent, to continental Europe. So that's what they are developing and working hard to get it done soon, because that's where they have now the energy. Their resources are wind power basically today.
Yeah. Thank you. And one question from the Zoom room, like from the, I think we are talking, which one is the best from these two HVDC technology? I think it's LCC or Hvac in terms of eliminating space charge phenomena.
Which?
Space charge.
Space charge.
I think when you have like high voltage DC, you can accumulate space charge in the line. So when I
think in that sense, it doesn't really make any difference, because the space charge due to the high voltage DC, it's going to be the same. It doesn't matter if the converter is VSC or is LCC. It's the voltage that creates a space charge. So it might be a 500 kV plus minus 500 kV bipolar link, and you will have the same DC space charge DC issue, because it doesn't really make the difference between LCC and VSC.
Yeah. Yes. One question, actually the last question from YouTube, which I think it's also interesting, the question, and quite relevant as a closing question in a way. A question about the human resource or competence. Like when we are handling HVDC system, does it require engineers with specific competence, training, or certification, probably compared to the HVAC classical technologies? And I personally would like to ask question, because I mean, for all the participants, that is actually what Dr. Gabriel Olguin has experienced personally, that you actually went back from Sweden, you have spent your PhD there, you have been working in the corporate research centers or one of the leading companies in power technologies. and you were actually going back to Chile 12 years ago to develop HVDC. And basically, that was the question about the human resource or competence. How do you see this HVDC system? Does it require new certification, training, educations, especially your personal experience, which is very interesting?
Yeah.
We are
My
talking
personal
about
experience.
Yeah, about countries where you do not have until now an HVDC. So please, I think feel free to expand your question, your answer here. Yeah.
Reza, this is a very important topic for countries like us, and I'm going to talk about my own country. We don't have the technology, and since we don't have the technology, it's very difficult to get at once. Say you have decided the project and you will hire people to develop the project. You won't get it. You won't get them because they are not trained. Exactly. They don't understand the technology. As I said in my previous conversation before, going live, I said 1% of power engineer knows Hbdc technology, but that doesn't mean that they cannot understand it. They need to go back to the fundamentals. And that's what I tried to do in this presentation. I went into the very fundamentals. Since 28, when I came back to Chile, I came to develop one of the projects that was supposed to become the very first Hbdc project. The project didn't fly. But since then, I've been, developing webinars, seminars, and talks and lecturing at the university. At one point, the university I was teaching decided to stop the Hbdc course because we didn't have any project. So they decided, okay, no, we're not going to give the Hbdc course. Now that the project has been announced and is going to be, sent for international bidding next year, I'm full of, offers to deliver courses, talk, and that's a pity because we should learn technology, not because it's going to happen tomorrow, but because we need to be prepared for the technology. It's the same with nuclear power. At one point, there was a huge debate about, developing nuclear power. That was maybe back in, I don't know, let's say 2010. There was a big debate about developing nuclear power, but we didn't have the engineers. So whenever you face a project like this project is 1.2 billion US dollar. That's more or less the idea. So if you're going to invest 1.2 billion US dollar in a project, you need to prepare your people. And that can be said that can be done by, let's say, universities, private companies, consultants, but it would be much better if there is a vision.
Yeah.
If the government or the authorities, they have a vision and they say, okay, this project is going to happen in 10 years. So let's promote the technology. Let's promote the learning process of our engineers so that they can fulfill all the requirements for this project to use local capabilities. Because I know that, Europeans and Americans can come to Chile and can develop everything that needs to be done in order for this project to succeed. But I mean, the idea is to be part of the project, to have educated people to say, okay, what if, at least good questions, smart questions. Because if we know nothing, then it's very difficult to participate. So at least in my vision is to prepare people for this project. And that's why I've been, delivering training and spending a lot of time going abroad and participating in courses. As I said, I'm also study committee before of SIGRE, which is very active in pushing forward the technology. We really challenge the vendors in solving the issues that we still see in the technology. And it's an international community, and we have people from vendors, we have consultants, we have engineers from independent system operator, from regulatory body, and we have very transparent and honest discussion about what can be improved. So it's a very technical forum to learn and to challenge vendors, but at the same time to challenge yourself and to learn more about the technology and the things that should be improved. What we are facing today in terms of energy transition is, it's something extremely powerful. Our system, the system I was showing you, was hydrothermal. Thermal in the north, hydro in the south and central part. And today, you wouldn't believe the amount of renewables that we are integrating, because we are rich in terms of solar power in the north. I mean, the highest radiation in the world is in the Atacama Desert.
Yeah.
So the amount of power that is being interconnected there in terms of PV, mainly PV, because it's extremely cheap in terms of technology, is huge. And that poses a lot of challenges like inertia, like short circuit, and those challenges should be addressed early, not late. So we have to be prepared for that. And it's happening everywhere. Peru is also moving in that direction. I mean, sooner or later, we will have to move, because that's what happened. And we will be integrating more and more renewables using converter-based technology, as you know, wind farms, solar, and also energy storage is also something that is happening. Energy storage based on batteries, on different technologies, battery today, eventually other technology like pump hydro and so on, will come into the picture, because the more renewables we integrate into the system, the more we need energy storage solutions. So it's important to build the capabilities, because we will face those projects, and the idea is to have engineers which are prepared to contribute to the development of those projects.
Yeah.
By the way, I share with you this vision of sharing knowledge, and this what you're doing is really interesting, and we need to discuss a little bit more, because I really like the idea of doing this.
Thank you. I mean, Gabriel, I'll be happy also to have knowledge sharing with you guys in Chile. And actually just, yeah, there are actually some questions, but I think we have like half an hour more. So I hope that you can join another expert class. I would be happy to listen about that renewables experience in Chile. And also the statement or the answers that you gave before, I think it's a very strong closing statements that the competence of the people are very important to develop the technology in our countries. And sharing knowledge is one of them. So even that we don't see the projects or the technology will be implemented tomorrow, it's always important to be prepared. And I would like also to I mean, it's a compliment to you actually, Gabriel, that you actually built you develop the knowledge, you develop your competence, and now even you are helping neighboring countries in South America in Hbdc technology. And that is, I think, also a good lesson for us in Indonesia, that when we are learning something, even the project is not necessarily implemented right away in the country, your knowledge will remain with you. And as you said, you can talk in the international communities, and you can actually contribute to the international communities, and you are helping even neighboring countries. That's a very strong statement, Gabriel. Thank you very much. And for the attendees, sorry for the questions. We have still some questions, but I think and I hope Gabriel will give another lesson for us, another lectures. And again, thank you very much, Gabriel, and thank you very much for the attendees, for the participations. And for your information, this is actually the one of 2 Hbdc lectures that we are organizing in Yo Berbagi expert class. So next week on Wednesday, and you are also invited, Gabriel.
Absolutely.
We'll have another friend of us, Kailash. Yeah, Dr. Kailash Srivastava. He will give lectures about Hbdc system modeling. And I think Gabriel and we know for sure how good Kailash is with power system simulation, modeling, etc. So don't miss the next course next week. And the time will be the same, Gabriel. So it will be like evening in Indonesia, morning in Chile, and afternoon in India, because Kailash will be from India. So again, thank you very much, everybody. Good evening and good day for Gabriel. Have a nice day and have a nice evening, everyone.
Thank you.
Selamat malam.
Bye-bye.
Bye-bye. Wassalamualaikum warahmatullahi wabarakatuh. Thank you very much.